Good afternoon, everyone. We are starting another lecture in the cycle of seminars from Astronomy Department at IAG. Reinaldo and Maria are on vacation, so today I am here. The seminar will be presented by Raniere. Raniere Menezes holds a bachelor degree in physics from the Universidade de Pernambuco, a master's and a doctor's degree in astronomy from IAG, where he worked with high-energy astrophysics using gamma-ray observation made with the Fermi Space Telescope. He's currently a postdoctoral researcher at the Istituto Nazionale de Fisica Nucleare and Astronomy at the Magic Telescope. His research addresses several distinct topics in high-energy astrophysics, such as the emission of hadronic gamma rays in AGNs, the formation of compact binary systems in globular clusters, and the characterizations of blazars at various wavelengths. So, as you already know, you can ask your questions in the end of the lecture via Google Meet, YouTube chat, or here. And also, whoever is following the meet, please turn off your microphone and your camera. So please, Raniere, you can start whenever you want.
Okay, thank you, Loreani. Thank you very much for the introduction. Let me know if you can see. Just a second. Let me know if you can see my slides. Can you see it in full screen?
Yeah, it's okay.
Okay, so hello everyone. Today we are going to talk about how the dynamical properties of globular clusters affect the gamma ray and X-ray emissions. First of all, I will introduce the Fermi Large Area Telescope, because this is the main instrument used in this work, although it's not the only one. The Fermi Large Area Telescope, that we call LAT for short, is subdivided in three main components. One is the tracker, that is made of 16 towers like this one, that once a gamma ray enters the tracker, it faces one of the 16 layers of the tracker and interacts to generate a pair of electron-positron. This pair of electron-positron then leaves an ionized track in the semiconductor layers of this detector, and we can use this path of this ionized path to reconstruct the incoming direction of the gamma ray. So the tracker is responsible for pointing. It points the direction where the gamma ray is coming from. Below the tracker, we have the calorimeter, which we use to measure the energy of the incoming photon. So once the electron-positron reach the calorimeter, the opacity is so high that a cascade of particles is developed. And then the calorimeter can image, it has a half image capabilities, and then it can take the shape of the cascade and say what's the energy of the incoming photon. And the last instrument is the anti-coincidence detector that covers the tracker, and it's a plastic scintillator. Every time that a charged particle crosses it, it releases a flash, and the telescope knows that what's going down the tracker is a cosmic ray and not a gamma ray. So you already noted that we are not converging gamma rays here. So in gamma rays, we cannot make a zoom in the sky. We can simply point the directions of the incoming photons. So Fermi-LAT has been collecting data for more than 14 years now. And in the latest Fermi catalog, the 4FGL data release 3, we have more than 6,000 permanent gamma ray sources in the sky. 25 of them are lacking a counterpart in other wavelengths. And this is one of the major problems of the Fermi collaboration, because the positional uncertainty when pointing the direction of the incoming photons is quite high. And so the resolution of a gamma ray instrument is not as good as the resolution of an optical telescope or an infrared radio. So what for Fermi is a point in the sky, when you look for at this point in other wavelengths, you can see several sources within the PSF of this point. So several times we don't know which of the sources within the uncertainty region is the responsible for the gamma ray emission that we are seeing. And in 4FGL, 60% of the sources are associated with blazars that you can clearly see here, some of them, the brightest ones, as the blue dots, especially far in the north and far in the south of the galactic plane. So all of these blue dots that you see are blazar associated to the gamma ray source in 4FGL. We also have non-blazar AGNs, about 200, and several other classes of sources like pulsar, supernova, remnant, pulsar wind nebula, some binary systems, and of course globular clusters, which are the main subject of this work. Okay, globular clusters are evolved collections of stars that are bounded by gravity, and just in taking a look at it, you can say that there is a high density of stars in globular clusters, and indeed the density is very high, so high that it's easy to find a globular cluster with more than 1,000 stars per parsec cubic parsec in the cores. So it's very common to find a globular cluster with more than 1,000 stars per cubic parsec in the central region only. And they are typically very old, so most of the globular clusters in the Milky Way have more than 10 billion years, although there are a few exceptions. And dynamical interactions in such an environment where we have so many stars compacted in a small volume are common. So dynamical interactions are really something common in globular clusters. 47 Tucanae was the first globular cluster detected in gamma rays by Fermi-Lat, and up to date we have 37 globular clusters listed in the latest catalog of Fermi-Lat. However, in this work, we expanded this list by 6 sources. We found 6 globular clusters that were never listed in 4FGL. Okay, globular clusters host several compact binary systems, which are binary with very short periods, typically a few days or less than a few days, less than 3-4 days, that have at least one compact object, like a neutron star or a stellar mass black hole, or even a white dwarf. And stellar flybys eventually produce these closed compact binaries, and eventually they enter on a mass transferring regime. When this mass transferring compact binary is made of a neutron star and a low mass main sequence star, it becomes what we call a low mass X-ray binary that are the progenitors of millisecond pulsars. And when I say low mass star, is a star with a mass is smaller than the mass of the neutron star. This is what we call a low mass X-ray binary. So it's important that the donor star is low mass because it provides a continuous and slow flux of matter from the donor to the compact object, and it is needed to have this continuous flux for hundreds of millions of years, such that the neutron star in this system can be spin up until it becomes a millisecond pulsar. So it's important that we have this configuration. Of course, there are other types of compact binary systems, but these other types typically don't evolve into millisecond pulsars. And okay, the gamma ray emission that we observe from globular clusters are actually coming from the populations of millisecond pulsars that they contain. So the gamma rays are generated in the outer regions of the magnetospheres of the millisecond pulsars, very close to the light cylinder. I don't know if you are familiar with the light cylinder, so I will do a quick introduction here. Imagine that we have here a neutron star and a dipole magnetic field. The magnetic field is so strong for these neutron stars. In this case here, a billion Gauss, around a billion Gauss, which is small if you compare to young pulsars, but is still strong if you compare with basically anything else in the universe. And for such strong magnetic fields, the plasma in the surroundings of the neutron star is frozen to these magnetic fields. So when the neutron star rotates, the plasma in the surroundings rotates with it as if it was a rigid body. So obviously that when we go to higher radius, if we have a rigid body rotating, at some point the rotational velocity will reach the speed of light. And so the gas, the plasma cannot rotate together with the neutron star anymore. And since it's frozen to the magnetic field lines, what happens is that the magnetic field lines will start to be open in this region that we call the edge of the light cylinder. And we don't know exactly what is the process emitting gamma rays in the magnetospheres of millisecond pulsars. But among the several models that we have, those that prevail are those that where the emission is coming from this region here, close to the border of the light cylinder. There are the models about the outer gap and models about gamma ray emission from equatorial current sheets. And they are competing, even today they are competing to see which model fits better the data. And the predicted gamma ray spectrum from this type of objects is a power law with exponential cutoff. So we expect that the gamma ray spectrum of a globular cluster, where the emission is coming from a population of millisecond pulsars, present a spectrum that is the sum of the spectra of several millisecond pulsars. And indeed, this is what we have. This is the gamma ray spectrum of Terzan 5, which is the globular cluster with the highest gamma ray flux that we have. And we have a power law with an exponential cutoff. So it's what we expected. And okay, continuing with the introduction, I have to tell you how we quantify the stellar encounter rates, because this will be crucial for this work. So the compact binary systems are thought to be formed in stellar encounters, but how we quantify it? We have this quantity here, gamma, that we call it the stellar encounter rate. It's the encounter rate for two single stars in a globular cluster. So it depends on the density of the globular cluster, which is a function of the radius, the numerical density of stars. It depends also on the dispersion velocity of the stars in this cluster, which is also a function of the radius, and it's integrated over the volume of the globular cluster. So this quantity here, which is very similar to those reaction rates in nuclear physics, is what we call the stellar encounter rate. But once a binary is formed, it can undergo subsequent encounters that can make the binary even harder or eventually ionize the binary. And this is the nomenclature that we use. We say that when the binary is disrupted, it's ionized. And the stellar encounter rate per formed binary is proportional to the density of stars in the globular cluster, inversely proportional to the velocity dispersion, and also depends on the orbital separation of the binary. So the larger is the binary, the higher is the probability that it will face another star in the globular cluster. And we need this parameter to state how important are secondary encounters in the evolution of binary systems. And this should be a problem, but it is not. And it's not a problem because in order to a binary system be formed in a stellar flyby, we need to lose energy in some way. So there is absolutely no possibility that two stars will come from the infinite, pass very close to each other, and be captured in a binary system if they don't lose energy in some way. They have to lose energy so that the final total energy of the system is negative. And when they pass very, very close to each other, when I say very close, it's about a few stellar radii, they induce tides in each other, and the energy of the system is dissipated by the tides. So in this case, we can have a binary system formed in a stellar flyby. However, the resulting binary system will have a final periastron of just a few stellar radii, like 3 to 5. And we'll have a very eccentric orbit. However, since these are compact binaries, the orbits are very short. So in a matter of one day or a few days, it will complete an orbit. And after a few orbits, these binary systems will tend to circularize very quickly. So in the matter of 1 year after the binary is formed, it depends a lot on the structure of the binary and on the internal structure of the stars, but it will quickly circularize. So in this work, we assume, to be conservative, that the final separation, orbital separation of the binary is 10 stellar radii, which means that this A we are assuming as 10 stellar radii, and I will come to that later. And, a typical star in a globular cluster has half the mass of the sun and roughly half of the mass of the sun. So this is quite a coincidence because we have 8 times less volume, but if we have half the radius of the sun, but in any case, this is just a happy coincidence that I start with half the mass of the sun has half of the radius of the sun. Okay, since I already gave you an introduction, I'm going to tell you what are the goals of my current work, and then describe what I found and where I'm trying to go. So these are the main questions and topics. We would like to do a spectral characterization of 124 globular clusters in the Milky Way and check if the gamma ray emission is consistent or not with millisecond pulsars. There are more than 150 globular clusters in the galaxy. However, for only 124, we have precise measurements of the stellar encounter rates. So we have that integral that I showed you a few slides ago, precisely computed using the profile, the density profile, and the velocity dispersion profile. So we are using this sample because it's the most robust sample that we have in terms of dynamical parameters. We also want to test if stellar encounters really contribute to the formation of compact binaries. Which I mean by that is that there can be other possibilities for a compact binary system to form, and we explore that in this work. And we also want to test what's the importance of secondary binaries, of secondary encounters once a binary is formed in the framework of the Heggie-Hughes law that I will introduce it to you later. And we also look for extended gamma ray emission from the propagation of leptons within globular clusters to see if we can put some constraints in the propagation of cosmic rays in this kind of object. Okay, for the first topic that we have here in slide 10, and kind of first question, is the gamma ray emission from globular clusters really coming from millisecond pulsars? And the short answer is yes. We, instead of analyzing one by one the gamma ray spectra of the globular clusters, we did a color plot. And this, I assure you, you will never find in the gamma ray literature. Especially because in gamma rays, typically you have a continuum sample of data. So people already have the spectral parameters and they are not plotting color diagrams that are more restricted when we are observing in bands, like we typically do in optical, for instance. However, I found them to be very useful for the classification of gamma ray sources. So in this plot here, you can see in the shaded areas, we have flat spectrum radio quasars colors. We have BL-LAC colors in this strip here. PSR stands for young pulsars, and MSP for millisecond pulsars. So we see that the globular clusters, almost all of them have colors consistent with millisecond pulsars. We have this exception here, that is Messier 15. However, this cluster is known for hosting at least 4 young pulsars. We don't know exactly what's happening in this cluster. But in any case, this is a very powerful, the color diagram is a very powerful tool to discriminate between classes of gamma ray sources. And we define a gamma ray color simply as the integral from a minimum energy to a predefined maximum energy of the differential photon flux. And we have 3 colors defined between 300 mega electron volts and 20 giga electron volts, which is the range at which globular clusters and millisecond pulsars are emitting most of its energy in gamma rays. An extra content about the colors. We recently found that these colors are quite good in discriminating the gamma ray sources. So this is a map that we did in São Paulo 1 year ago, I think. And we did it for fun. But in the end, we found that the colors in gamma rays, they are very strong in discriminating between different classes of sources. Like in blue here, in the top and in the bottom especially, we have the blazars. These red yellowish sources in the close to the galactic disk are typically young pulsars. And we have some green sources here and here in the bottom that stand for globular clusters and isolated millisecond pulsars. So I think that using colors in gamma rays is something that should be done more often. And I think that it has a huge potential, especially for machine learning association algorithms. So this is something that I would like to explore in the future. But let's keep going. So individually, the spectral energy distributions of globular clusters are well fitted by a power law exponential cutoff, which is given by this formula here. And so in some few cases, we can see an excess of gamma ray emission above 20 giga electron volts, which could be really exciting for Cherenkov telescopes. But this is also something that I'm going to keep for another project. Okay, so question number 2. Are the stellar encounters really contributing to the formation of compact binary systems in globular clusters? And the short answer is yes. And I really like this plot and I really want to discuss about it. So in the y-axis, we have the number of X-ray sources in the central region of globular clusters versus the stellar encounter rate that I showed you before, that is given by this formula here. So we see a very tight correlation between the total number of X-ray sources that we count in globular clusters and the stellar encounter rate. And the inclination of the fit is 1, is consistent with 1, which is exactly what we expect. So the most stellar encounters we have, simply the most compact binaries we have. It's a linear correlation. And this plot has a lot of information. So I tested if the number of X-ray binaries depends on the stellar encounter rate, and the answer is yes. And I also tested if we could use if primordial binaries could evolve slowly due to stellar encounters, and the primordial go to shrink until becoming a compact binary system. So this color bar here gives the shrinking time scales for primordial binary is starting with an orbital separation of 1 astronomical unit and going down until IAG-W, which is the gravitation, the orbital separation where the gravitational waves dominate the loss of energy. So you can see here that for most of the globular clusters, the time scale for a primordial binary with this configuration is actually longer than the Hubble time. Just for a few of them, it's lower than smaller than the Hubble time. But so we found that it's completely inefficient that a primordial binary will shrink due to secondary encounters until it becomes a compact binary system. So we tested two scenarios in this plot. For the first, the result is very positive, and for the second, the result is negative. And okay, I told you that in the y-axis, we had the number of X-ray sources in a globular cluster. And however, we cannot simply count, like put the finger in the screen, 1, 2, 3. It's not like that. We have to be more careful because there are lots of background X-ray sources, and we have to take them into account. So we are using this relation here, that is the log n log s relation for hard sources in Chandra, which gives us the number of sources expected per square degree of the sky, which compounds the background. So what we do in the end is counting all the sources and subtracting the number of expected sources from the background. So in the end, we have a more reliable estimate of the number of sources of X-ray sources in the globular cluster. We have also an extra problem because we are using this data for this X-ray data from Chandra. So the observations that are performed with Chandra, they are not even. So some globular clusters have deeper exposures than others. So how can we count the X-ray sources if we have different exposures, right? So we are setting a luminosity limit for all globular clusters and say, okay, if Chandra could reach this luminosity limit in this cluster, we take it. If not, we skip it. And indeed, Chandra observed more than 70 globular clusters, but I'm not using all of them here. I'm using way less, I think 30 something, because only these clusters reach the required luminosity in this work. So doing the same thing in gamma rays, we have this plot. And here we see that the The index of the fitted power law is also 1, so it's good. However, we see that the scatter is quite big. It's not like in X-rays. And this, I think, and this is what I'm writing in the paper, that's because in gamma rays, the emission is beamed, while in X-ray, no. In X-ray, it's way more isotropic. And here we even have some upper limits. All of these gray upper limits here are for the 124 clusters that we analyzed. And we see that some upper limits even break the fit. The magenta upper limit are even more special because we have at least 5 millisecond pulsars detected in radius in each one of these magenta points. And these ones that break the fit would be concerning, but I think that this is just an issue of orientation of the pulsars. And since our samples are not that big, we can have strong fluctuations. But indeed, at least we still have the same inclination as we find in X-rays. So let's go to question number 3. How do once the binary is formed, how do secondary encounters affect the evolution of these compact binaries? And again, the short answer is that they make the binaries harder. And I think that this is the most interesting result in this work. However, to get there, I have to introduce you to the Heggie-Hughes law. It's not stated exactly like that by Heggie and Hughes, but this is how you find nowadays in the literature. So hard binaries tend to get harder and soft binaries tend to get softer in face of three-body encounters. Okay, but what's a hard binary? We have a hard binary every time that the binding energy of the binary system is larger than the typical kinetic energy of the surrounding stars. And the binary is soft if the binding energy of the system is smaller than the typical kinetic energy of the nearby stars. This is how we define hard and soft binaries. Okay, just substituting the binding energy here by the extended formula, we can isolate the orbital separation and say, okay, if the binary within a globular cluster has an orbital separation that is smaller than this quantity here, then the secondary encounters will make the binary shrink. And we can rewrite it in terms of the stellar encounter rate that I introduced you a few slides ago. And we can write the normalized stellar encounter rate as this quantity here. So the normalized encounter rate per formed binary, if larger than 1, the binary will be ionized. If it's smaller than 1, then the binary will tend to shrink and shrink even more. And this is the result that we get for the globular clusters detected with Fermi-LAT. So the secondary encounters make the binaries harder. And I say that because the lambda that I just defined, the normalized encounter rate per formed binary, is very, very low if compared to 1. So here the lambda is 10 to minus 3 typically. And then the stellar encounters will make the binaries harder and harder. And for that, we are assuming, as I told you a few slides ago, that the initial orbital separation of the binaries is 10 stellar radii, and that they go down until RT, which is the tidal radius, the Roche limit. I never know how to pronounce the name, but the Roche limit. So the star will be disrupted when it reaches the Roche radius. And for half of the clusters, actually, the binaries orbiting at this distance from each other lose more energy via gravitational waves than from stellar encounters. And don't think that I'm saying that this is an effective way of losing energy, because at 10 stellar radii, the amount of gravitational waves emitted by a binary system is not that great. So, but it's even at these conditions, it's higher than the amount of energy lost via stellar encounters. This is just repeating what I said. So the secondary encounters make the binaries harder, but not that much, because the time scales involved are very, very long. And in the end, both time scales, the stellar encounter rate and the gravitational wave emission, are very long. So we have a problem analogous to the final parsec problem for these compact binaries in globular clusters. But okay, we found that the secondary encounters make the binaries shrink even more, at least in the globular clusters that we analyzed with Fermi. Okay, the last point of this presentation is the investigation of the extended emission in globular cluster. And do we observe extended emission? No, we don't. But maybe because Fermi is not the optimal instrument for doing that. We probably have to wait for CTA to have some answers to this subject. So a handful of globular clusters in our sample have a half-light radius that is larger than the resolution of Fermi-LAT. So in principle, we could detect them if they were emitting, if the central regions at least were emitting gamma rays halfly homogeneously. So we found no strong evidence for extended emission in globular clusters, like you see here that the extended radius of the source is 0.03, but the TS, which gives us this is the square of the significance, is only 0.3, so it's negligible, absolutely negligible. And to do this kind of analysis, we are not using a standard Fermi-LAT analysis. We are really going to the limit of resolution of Fermi, going down to 0.02 degrees per beam in the sky, and using only photons with more than 1 gigaelectron volts, that are photons that we have a more precise pointing with the tracker. The higher the energy, the better is the resolution. So in the end, globular clusters are point-like sources for Fermi. And this happens because the pulsars sink to the center of the globular cluster quite fast via dynamical friction. And they can do that alone, or they can do that already in a binary system. So the binary system is heavier than the stars in the surroundings, and it will sink to the bottom quite fast. And when we repeat the analysis for the 5 globular clusters with the largest half-light radius in our sample, we have these results. So the R is the radius of the disk that we are trying to fit to these globular clusters, and they are quite small. None of them is exactly significant. However, when we compare this sample of globular clusters with a sample of blazars, which are for sure point-like sources, we see that the R68%, the containment radius of the globular clusters, are typically higher than the radius of the blazars. So maybe when doing the study of the population, we can find extended emission in the population of globular clusters. However, even if we sum the significance of these 5 clusters, the final significance is not high enough to make conclusions. So this is something that I think is interesting, but is interesting for the future. And when I say the future, is not with Fermi-LAT anymore. I think we really have to wait for CTA to do something with respect to this. So the results are kind of expected because of the dynamical friction. So why are we looking for extended emission in globular clusters if they are expected to be concentrated in the cores? So there is another mechanism that's indirectly related with the millisecond pulsars that can generate gamma rays in a globular cluster. And the emission that we observe with Fermi is coming from the outer magnetospheres of the pulsars. However, some electron positrons can escape the magnetosphere of millisecond pulsars and propagate within the globular cluster. And eventually they will interact with a thermal photon from the surrounding stars in a globular cluster. Like here, we have a star, and we have an incoming electron or a positron, and it will interact in the photon, the star, and upscatter this photon to gamma rays. So you see it in gamma rays. So depending on the propagation of these electrons and positrons within the globular cluster, we can see some extended emission in the cluster. For instance, if the propagation allows the electrons to move beyond the half-light radius, so we can see some of this emission as extended emission. And these are some predictions for gamma ray emission from stars that we did in other paper that are very useful in this situation. However, we could not observe it, not yet at least. Okay, I'm about to finish. This is just to continue this example here. So this is the gamma ray emission from the sun, where we have two components: the disk emission given by this pink curve, and the halo, the solar photon halo emission given by this green curve here. So when summed, the gamma ray emission from the sun has a diameter in the sky of more than 30 degrees. So the sun is by far the largest gamma ray source in the sky, except for the Milky Way, of course. And we would expect to see some of this extended emission from globular clusters. However, this emission is expected to be seen more efficiently in the very high energy domain, which means with ground-based gamma ray telescopes. So we tried with Fermi, but Fermi is not exactly the recommended instrument for this kind of observations. And just going back to this slide, if we try to do this same plot in very high energies, then we would expect this correlation to be tighter again, like we see in X-rays. Because in the Fermi band, the gamma ray emission from the pulsars is beamed. So it's hard to have a good isotropic luminosity. However, in very high energies, since we expect the electrons to first propagate within the cluster and then interact with the photons to emit the gamma rays, we expect to see a more homogeneous emission of gamma rays. So the globular cluster is expected to have is expected to be well described by a isotropic gamma ray luminosity. And that's it. Before concluding, I'll just make some advertisement of Easy Fermi, which is a software that I developed for that uses FermiPy to do Fermi analysis, but to make it really easy. So if you want to use gamma ray data in your analysis, please give it a try to Easy Fermi. It's really easy to use. You can quickly compute a spectrum for your gamma ray source, create a light curve, or measure extension, like I showed you a few slides ago. And it's very straightforward to use. there are tutorials on GitHub and on YouTube. So give it a try. Yeah. And that's it. This is my summary. So the gamma ray spectra of globular cluster is indeed consistent with millisecond pulsars. So the people were trying some more exotic models in the past, like emission from intermediate mass black holes in the clusters that could generate a non-thermal signal that is not exactly following the spectrum of millisecond pulsars. Some people were trying to work with dark matter annihilation in globular clusters, but no, the spectrum is consistent with millisecond pulsars, at least for most of the clusters. The gamma ray colors are a powerful tool for discriminating different classes of sources, and this is not exactly a result, but it's something that I would like to do. I would like especially to chat with Rodrigo at some point, because I think that this has a lot of potential, especially because there in IAG, I know that there are lots of people working with machine learning, people that are way better than me in machine learning that can do that. We found that compact binary systems are indeed formed in stellar encounters. Maybe they are not, this is not the only channel for the formation, but we found that the stellar encounters form compact binary systems. And that in X-rays, we see it much better just because the emission is more isotropic than in gamma rays. And this is what I think is the major result of my work, is that secondary encounters of a formed binary in globular clusters actually shrink the binary, and they do not ionize the binary systems. And we found no evidence for extended gamma ray emission, although Fermi is not the best instrument in this case. And finally, easy Fermi is very easy and very powerful. Give it a try. Maybe you are trying to do an SED and you want to put some extra points in the high energy domain, and then you can simply use easy Fermi to be very straightforward. And that's it. Thank you very much.
Thank you very much, Raniere. Let's start the question section now. Does anyone has a question here?
Reinaldo has in
Okay.
the Google Meet.
Thank you a lot for the talk, very clear. I got very interested in your explanation of the colors in gamma ray colors, and I'd like you to tell us something if this color analysis can you connect somehow with the spectral index of the sources. It's not very clear for me if, for example, this color diagram, is it reflecting the spectral index of the source? Is it so? What you define as C is like the filter of some bandwidth, and when
Yes.
we take the difference between bandwidths, would it reflect the spectral index?
Okay, so you see here V, R, and B, right?
Yes.
These are the colors that I substitute here for C. So for instance, R, which is the redder, I will put here R instead of C. It's just the same thing. And I will integrate from 300 megaelectron volts up to, I don't know, 3.5 gigaelectron volts, something like that. I don't remember exactly what are the limits. But C just stands for colors. So V, R, and B are just other ways of writing C with different integration limits. And you asked if the colors reflect the spectral index, and yes, but there is more than that, because these spectra have a cutoff, and so these colors, they reflect the spectral index and the energy cutoff. So there is more information than just the spectral index. And very good that you asked that, because here for the BL lacs that are all modeled with, these are modeled with log parabolas. you can see that they are very concentrated in this region here. Because in the energy range that I'm adopting, the log parabolas used for BLAX are almost a power law. So for the BLAX here, the colors are basically telling you the spectral index. For the other classes, they give you more than that. They give a spectral index and curvature and the cutoff.
Thank you. Really, it's a very interesting analysis. I think I agree with you. There is a lot to be done there, to be explored. Yeah, it's really interesting.
Thank you. Thank you very much.
Naming, please.
Hi, Raniere. Excellent presentation.
Thank you.
You mentioned that the Tarzan 5 is the only globular cluster that has been observed in very high energies. So I think I perhaps missed during your presentation. But what is the observatory that saw it in very high energies, and what is special about the source that it shines in very high energies?
Okay, the observatory was HESS, and currently HESS is the best one for doing observations of globular clusters in very high energy, simply because it's in the south. MAGIC and VERITAS are in the northern hemisphere, and most of the globular clusters are in the southern hemisphere because they are typically in the same direction of the galactic center. And you asked why Tarzan 5 is special. Tarzan 5 is the globular with the highest flux in the Fermi-Lat band, and is the globular cluster for which we have the highest number of millisecond pulsars detected in the radio. So this is indeed a record-breaking globular cluster in our galaxy. I have a slide here, this one, that I say that 47 Tucanae was the first globular cluster detected by LAT. And indeed, it was the first because the TS of 47 Tucanae is higher than the TS of Tarzan 5. However, the flux of Tarzan 5 is higher than the flux of 47 Tucanae. And this happens just because of the position in the sky. While 47 Tucanae is very isolated, very far from the galactic disk, Tarzan 5 is in the bulge of the galaxy. So for Fermi, it's harder to distinguish it because we have more background. So just because of that, the TS of Tarzan 5 in Fermi is smaller than the TS of 47 Tucanae. But in the end, the flux of 47 Tucanae of Tarzan 5 is higher. It's the highest flux that we have for a globular cluster. And this is what the number of millisecond pulsars is what makes it special for the observations. This is indeed the best candidate, in my opinion, for Cherenkov telescopes.
Professor Laird, you can go.
Hi, Raniere, very interesting talk. I have a couple of curiosities, actually. Why the blazars are observed outside the plane, in the pole regions? This is a bit strange for me.
Go back. So here, why the blazars are in the poles? No, because far from the galactic center, we have less background, and it's easy to spot the extragalactic sources. So for high galactic latitudes, we basically only have blazars.
I see. It's only a selection effect then.
It's a selection effect, exactly.
Okay. The other point is, please go to the color diagram that this one. How do you manage to measure the colors of stars in the globular cluster? I ask it because they are mixed. I suspect that in the they are highly contaminated, no?
Okay. These are not the colors of the stars individually. These colors here are the colors of each globular cluster. So
Ah,
For this point here, for instance, which is I know this one especially because this is the outlier. This is Messier 15. So this is the color of the globular cluster in gamma rays. It's not
okay.
of the individual stars or pulsars individually. It's the gamma ray as a whole,
Okay.
the globular cluster as a whole.
Mhm. Okay, thank you.
Okay, so hi Raniere. We still
Hi,
don't
Gio.
we still don't have questions from YouTube, so I will make my own questions. So I have two questions regarding the emission of gamma rays in millisecond pulsars. So first of all, how exactly occurs the interaction of the plasma in the magnetosphere of the stars with the light cylinder? Yes, that plot. And the second one, the model for the emission of gamma rays in current sheets that you mentioned in the equatorial plane of the millisecond pulsars relies on the magnetic reconnection process.
Okay. So let's start with your first question. How the process happens here? The exact channel for the gamma ray emission is still under debate. So the one that I have more familiarity with is the outer magnetospheric gap emission, where we have gamma rays from curvature radiation that I don't know if you are familiar with. Curvature radiation looks like synchrotron, it smells like synchrotron, but it's not synchrotron. So in this case, we have the charged particles frozen in the magnetic field lines. And when they open here in the edge of the light cylinders, these particles can escape, and they are accelerated by these extremely high voltages. So, but since they are frozen to the magnetic field lines, they have to follow the line. And when they do the curve, they emit what we call the curvature radiation. And the major difference for this, in this radiation is that the peak is shifted towards very high energies, like GeV, while in synchrotron, most of the cases we have the peak is in radio or infrared. And the polarization of the radiation is parallel to the magnetic field lines, which is exactly the opposite for synchrotron, right? Where we have the polarization perpendicular to the magnetic field lines. So this is the mechanism generating gamma rays in the outer magnetospheric gap model. For the current sheets, I have to tell you that I don't know, because I didn't know about that until a few weeks ago. And then I presented this work in the Fermilab collaboration, and they said, okay, we are doing these new models about the current sheets, and looks like they are looking very promising. But I unfortunately had no time to take a deeper look at them. So I don't know how magnetic reconnection can be related with the current sheet emission.
Okay, thank you. Any other questions? So I think we can thank you again, Raniere.
Right, thank you.
And due to the pandemics, we do not have coffee break today, unfortunately.
Okay, thank you.